An astrophotograph is a four-dimensional image. Think of it like this. An ordinary one-frame photograph relates the information from a single sliver of time. But these days, astrophotos are made out of many photographs called subframes, each on its own a single image carrying the information from a little sliver of time. The more slivers you have, the more information you have to work with. When we put all that information together in a process called stacking, we are bringing, in a very literal sense, information captured across multiple slivers of time together into a single final image. Ipso facto, an astrophoto is compressing 4 dimensions of information into a 2-dimensional presentation, something we call a photograph. Now the truth is, all photographs, even common photography right here on Earth, capture information in the form of light across a sliver of time. But with typical photography, we capture a single sliver of time in a single frame of image, whether that's a photo of the family dog or some lovely wildlife. And of course there is video, which captures many slivers of time and then presents them stacked one after the other, so that each photo portrays a segment of events that occurred across time. Now in astrophotography, we have the same goal as in still photography, to capture enough information to portray an image in a certain amount of time. Interestingly though, we do this in a way very similar to the way video is made. Throughout the night, we shoot subframes, capturing many slivers of time, one after the other. And in this sense, you could say that astrophotography resembles videography. However, instead of assembling the sequence of images into a video wherein one frame is presented after the other in rapid succession, creating the illusion of motion, all those slivers across time are brought together, combining their information to create a new, detail-rich photograph. And astrophotography is done this way because there are numerous advantages to shooting short subframes. If a region containing a deep sky object has particularly bright objects contrasting particularly dim objects, short subframes allows us to limit the amount of information we capture, thereby not blowing out the bright objects. And if something goes wrong while shooting one of those short subframes, such as a bright aircraft passing between the deep sky object and the telescope, forcing us to have to discard that subframe, then we are only losing a small sliver of time out of the total night's imaging. And if your observatory experiences anything unusual, maybe alien visitation, you can discard those images before anyone thinks you crazy and lose very little imaging time in doing so. But deep sky objects are extraordinarily dim. Their light comes to us from hundreds, thousands, or potentially even billions of light years away. And unlike with earthbound photography, the deep sky objects that we shoot are in fact so far away that their light trickles down into the telescope and onto a camera sensor, photon by photon, like drop by drop. In fact, the light from those distant deep sky objects is often so dim that it can take many hours, even multiple nights, to capture enough light to get enough information to create a single image. Because of this, in the old days of astrophotography, when mighty telescopes were imaging with photographic plates, and local amateur astronomers were using rolls of film, they took one shot per image and exposed for as long as possible. That is to say, as long as the sky was clear and their mount could accurately follow the object, in hopes of collecting enough photons to create an image. But in modern astrophotography, we shoot in slivers of time that can be as short as fractions of a second. Though usually they're a bit long, 30 seconds, a minute, maybe even 5 or 10 minutes in some cases. The images created in these slivers of time are called subframes. But if they have so little exposure time, how do they manage to ever capture enough light at all to create an image? After all, wouldn't they need more exposure time? Intuitively, you would think so. But even astrophotographers who use a technique called lucky imaging, in which the slivers of time they shoot are extremely short, tiny fractions of seconds, manage to gather enough information to make sharp and detailed images of deep sky objects, including distant and faint galaxies, objects that are millions of light years away. So how do such short subframes ever gather enough light to produce any information to contribute toward an astrophoto at all? That, my friends, is the question we're going to try to answer today. Because there is a considerable amount of debate and misunderstanding about this in the astrophotography community. And some persons who do astrophotography utterly refuse to believe that short subframes can capture such images, even after they have seen those images with their own eyes. And I get it. After all, everybody who does any kind of photography knows that when a subject is dark, you have to expose it longer in order to capture more light, right? The idea that you can shoot shorter exposures and still catch very, very faint objects and reveal even their dimmest detail, the idea is, to put it simply, highly counterintuitive. It would not seem to make sense, but the problem is we have to stop thinking in terms of the individual subframe and think in terms of the stack we are creating. Let's look at what happens when we stack a bunch of those subframes, or slivers of time, together. Dead center of this photograph that we have been looking at is galaxy NGC 7497, a very, very distant target, with a distance approximated to be 270 million light-years. It has an apparent magnitude between 13.5 and 14.2, classifying it as an extremely faint object. Literature recommends telescopes of at least 10 inches aperture in order to film it well. I shot this with a telescope with 8 inches of aperture. In point of fact, a Celestron C8 with 203 millimeters of aperture. The cloud-like structure you see surrounding it is called Integrated Flux Nebula, or IFN. This is nebulous material that may exist within or outside of our galaxy, but is distant from other stars, so its source of illumination is the combined light, or flux, of the Milky Way galaxy. Integrated flux nebulae are among the faintest structures to be found in space, and the IFN around NGC 7497 is about magnitude 24.5 per arcsecond, meaning it is vastly dimmer than even that distant galaxy. And this image was entirely shot using short subframe exposures of 60 seconds, with a Player 1 Aries M camera set for unity gain. It took 25 hours of shooting to capture 18.8 hours worth of good integration after calling for things like occasional clouds blocking the camera or sudden winds causing the telescope to vibrate. The old way of shooting astrophotography, back from the days of film and photographic plates, was to expose and try to capture the entire image all at once. A telescope would be pointed at the target, and the film would slowly collect photons over minutes or hours. Provided no issues ruin the photon collection process, at the end of a set period of time, one would wind up with enough photons to make an image. But in reality, were one to try to image a DSO with a single exposure lasting hours, that attempt would almost certainly be ruined by those problems we discussed earlier: tracking errors, guiding errors, wind-introduced vibrations, wildlife, aircraft and satellites, and anything else. Astronomers and astrophotographers long ago learned this, and thus, with the advent of digital photography, and with it, the ability to create images that are comprised of many shorter length exposures, shooting stacks of subframes became standard practice. Now let's look at how we would capture this image using modern techniques, shooting multiple subframes, but this time let's use long exposure times, say 15 minutes per subframe. The telescope and camera are once again pointed at our deep sky object. And, just as before, photons begin to trickle down through the telescope onto the camera sensor. Because these subframes have long exposures, each subframe builds up a fair amount of information. And at the end of total integration time, that's the complete amount of time the image is shot, all the subframes are graded for quality, and those that survive grading are merged together in a stacking application into a single master image, containing all the information captured among the various subframes. It is a process that works beautifully, but in many ways, this form of astrophotography is just like the old single-frame astrophotography, because while in long subframe exposure astrophotography, we are indeed creating subframes for a stack, we are still thinking more or less in terms of single-frame astrophotography, operating on the idea that we have to convey all the detail and all the bright and faint regions onto each subframe. In other words, in long subframe exposure astrophotography, just as with single frame exposure astrophotography, we are exposing for the frame. But in short subframe exposure astrophotography, we are exposing for the fourth dimension, time, or in other words, we are exposing for the stack. This is a highly counterintuitive concept, and I think it's best to illustrate it. Let's imagine our telescope and camera are pointed at a very dim, very simple deep sky object. The region on the left is very bright, the region in the middle is of moderate brightness, and the region on the right is quite faint. And we have decided to image this using a very short subframe exposure astrophotography technique, wherein we shoot 1 second per subframe. Now, let's imagine the brightest area emits 1 photon per second. The area of moderate brightness emits 1 photon every 2 seconds, and the faint area emits 1 photon every 5 seconds. We'll place a camera sensor under the deep sky object and begin imaging for 10 seconds total integration. But remember, we are using 1 second exposure time subframes. Ten 1-second exposures will yield 10 subframes. We can visualize the information each subframe carries like this. Each square represents a subframe. Every subframe received a photon from the brightest area of the DSO. Portrayed in the left of the subframe corresponding to the position of the brightness in the DSO. But only every other subframe received a photon from the mid-brightness areas of the DSO, and its position on the middle of the sensor corresponds to where it appears in the DSO. And only 1 in 5 subframes received a photon from the dimmest areas of the DSO, and where that photon lands on the sensor also corresponds to where the dimmest part of the DSO is. Take note that in each subframe, the sensor receives no more than 1 photon for any part of the DSO structure, regardless of whether it is recording the brightest, mid-bright, or faintest regions of the DSO. Now, a digital camera sensor assigns brightness based on how many photons are received by each part of the sensor. Photons land in the camera sensor's photosites and become an electrical charge which is measured. This electrical charge is an analog value which is converted into a digital value, known as an ADU, or an analog to digital unit. We won't go into ADUs here, it's a complex topic for another video. For right now, the key thing to bear in mind is that in our subframes, no part of the subframe, whether it's relating the brightest or the faintest information, receives any more than 1 photon per subframe. This means that in each individual subframe, the brightest regions of the DSO would exactly match the dimmest regions of the DSO. But if all the information is of uniform brightness, then we will not be able to record any detail, because detail is related by the differences in brightness between structures within an object. And this is the point where we have to think of exposing for the stack. We have captured information across the 4th dimension, time. We will not see the true detail captured until we bring all the information across time together. In 10 seconds, we shot 10 1-second subs. We put them into our stacker application, and it adds and averages all of this information together. One region of every individual frame got a photon, so when the individual subs are stacked together, the resulting master will show that region as brightest. Those regions of the image that got 1 photon every other frame will all be added and averaged together in the stacking software, which, upon counting 1 photon every other frame, will assign a mid-brightness level to that area of the image. And the areas of the image that got only 1 photon every 5 frames, when they are all added and averaged together in the stacker, will be assigned a faint brightness level. In this simple example, we see that it is not necessary to capture all the information in each subframe, nor is it even possible nor necessary to show distinct differences in brightness nor detail in each individual subframe. A tiny sliver of information per subframe is adequate. The true power of stacking is that it allows us to assemble information across time, fundamentally compressing the 4th dimension together. A person can shoot single-frame astrophotography and expose for the frame, or they can shoot subframe astrophotography, exposing for the subframes, or they can expose for the stack, allowing them to take advantage of the full potential of stacking by shooting short exposure times that will inherently be less affected by sky and mechanical aberrations, by shooting individual subs which in themselves may show little detail, but when stacked together show great detail with extraordinary crispness and clarity. If the subframe's exposure time is sufficient to capture enough photons to make even 1 single ADU per exposure, when enough subframes are shot, all that information can be added and averaged together to make a complete image. For those that are more technically savvy, a question will arise, but what about noise? If only a few photons are captured, leading to only a very faint trace of information, How can a subframe distinguish noise from signal? Once again, we must turn to what happens in the stacker. From the perspective of the individual subframe, it may be impossible to tell if very faint signal is any different from noise within an image. But noise appears randomly throughout an image, filling the gaps between information. Signal, on the other hand, is much more consistent. And when we shoot a bunch of subframes and then put them together in a stacker, that consistent signal stands out more and more. With every frame, the signal is added together. But because noise moves around, it does not add together frame to frame very well. So, the signal becomes stronger as information is stacked, while the noise becomes averaged out, and eventually, the noise is drowned out in the signal. Even if you couldn't tell signal from noise in the individual subframe, in the stack, it stands out. And the more subframes you have shot, the more clearly it will do so, because that provides more samples to assess and determine a clearer and clearer picture of what is signal versus what is noise. Now, if you're going to shoot extremely faint objects, perhaps even dimmer than IFN, you may get a bit better signal-to-noise ratio with somewhat longer subframe exposure times. But astrophotographers need to think strategically and consider the advantages of those long subframe exposure times versus their disadvantages. In my way of approaching astrophotography, I think it's only worth it to shoot longer subframe exposure times if I'm specifically trying to shoot an extremely dim target, and I know atmospheric conditions are likely to be ideal. And even then, I would only do it if absolutely necessary. When pondering the choice between whether or not to shoot long exposure subframes or short exposure subframes, there is most definitely more to consider. For example, if you live in an urban environment, light pollution makes some of the decision for you, because subframes can become subject to light pollution as exposure time increases. And shooting short exposure time subframes will generate hundreds, even thousands of subframes in the end, which some persons argue they don't want to have to deal with. They don't want to spend the time assessing them or the time stacking them, and it is time intensive. Though, in my opinion, it's not that bad. I've covered grading and calling extensively in previous videos, and I can tell you from countless hours of experience that in a typical night, I'll end up with about 600 subframes, or 10 hours worth, since I typically shoot at 60-second subframe exposure time. It takes me 10 minutes, give or take a couple minutes, to visually grade them. Though bear in mind what I'm doing is very simple. I'm using a program called View, just to make sure there are no clouds in the image, no double exposures, no weird things that grading software isn't going to know how to recognize, such as an owl sitting in front of the telescope. And then I run the subframes through the subframe selector in PixInsight and let it do the final calling. As to stacking, my previous computer, which I bought 5 years ago, took about 6 hours to stack 1200 subs. But computers have gotten so much more powerful. The new computer that I just bought about 2 months ago will stack them in an hour, give or take a few minutes. As I've noted in many previous videos, to me the extra effort is worth it. After all, imaging a DSO is a time-consuming and demanding process. It requires waiting for the DSO to be in a good position and hoping the weather will cooperate at that time, as well as developing significant expertise in dealing with telescopes, managing your mount, running the sequencing software, and using multiple applications to grade and develop the final imagery. It is not uncommon that it takes me several weeks to a couple months to complete imaging a DSO. And I have some ongoing projects that I started over 2 years ago that I'm still waiting for conditions to become right again to finish them. So the way I look at it is, if I'm going to put all that effort into it, why skimp by shooting longer subframes when I know that short subframes are going to provide superior results and make better use of my time? I hope this has helped you to come to understand the advantages of shooting short subframe exposure times and how it is that short subframe exposures can still manage to capture information from extremely faint and distant deep sky objects. The fundamental is basically, when we shoot long subframe exposures, we're exposing for the subframe, but when we shoot short subframe exposures, we are exposing for the stack. And as exotic as it might sound, this means that in literal reality, an astrophotograph is an emergent result of compressing the fourth dimension, all the information captured across time, into a single image. Let that blow your mind and get out there and shoot the sky.